here. So without further delay, let me give a very brief introduction of Shubham. Thank you, Shubham, for accepting our invite to share your knowledge about the post-processing techniques using Python. So Shubham Goswami is a PhD scholar in the University of Alberta. I think he is a senior PhD scholar going to finish his thesis very soon. And he is very much active in sharing the OpenFOAM knowledge through his Medium articles. And so I invited him to share his knowledge on the post-processing techniques of OpenFOAM data using Python, which came up in discussion of yesterday's that how we can post-process data efficiently. So without the further delay, I request Shubham to start with the training session.
Sure. Thanks, Dr. Bose, for inviting me. So today I'll present a brief workshop on advanced techniques for analyzing OpenFOAM data using Python. Just to give you a background of where this workflow comes from. So since I started learning OpenFOAM and started using OpenFOAM about 8 years ago, I was trying to look for methods to basically tag OpenFOAM with Python because that was the programming language that I was learning at that point. So I wanted to basically develop a workflow kind of so that I can basically efficiently analyze my simulate things in OpenFOAM and just visualize and analyze it in Python. So the idea behind this technique was basically to bring together a CFD powerhouse, which is OpenFOAM, and data analysis powerhouse, which is Python. So Python offers these powerful built-in modules, such as NumPy, SciPy, Matplotlib, FluidFlow, and PyVista. It is also interactable and portable in the way that you can explore things by basically running those block scripts in Jupyter. And OpenFOAM, apart from it being this wonderful CFD powerhouse, it offers two amazing features that I absolutely like. So first, it has a lot of function objects. So it has a lot of built-in post-processing functionality through function objects. And second, it has an amazing command line functionality that I basically use on a daily basis. So where this workflow comes from, it comes from certain constraints that I set for myself when I started my research. First and foremost, I wanted to basically work on data that was stored on these high performance computing clusters. So the idea there was that I set up my case locally, upload it to an HPC cluster, do all my pre-processing step till decomposition, and then run my case. And when my OpenFOAM simulation ended, that's where my problem started. So first of all, locally, I didn't have enough power to store it or even analyze that data. So I wanted to come up with a easy way at that point where I can basically work with HPC stored data directly in terms of basically exploring data and visualizing data fast, like visualizing and analyzing the data really fast. Uh, in terms of visualization, what I aimed for is not to use ParaView, Visit, or TechPlot. I wanted a more simpler way. Now, all of these three tools, they're really vast in terms of their functionality, but I wanted to get something simple. So for me, Matplotlib was the simplest plotting tool that I use. So I wanted to do something with Python at that point. And moreover, I didn't want to change or add anything to the source code anywhere. So I wanted to create a smooth simulation to analysis workflow. And basically using all these constraints, I came up with this workflow that has been working for me since last 8 years now. So just going into a bit of background before starting the training, there have been a lot of projects that have brought together OpenFOAM and Python previously. But how this workflow differs from others is that, first of all, it's only a post-processing implementation. So I'm not changing anything in the source code, nor in Python or OpenFOAM. I'm not adding anything in the OpenFOAM uh, header or C file so that I can tag, like I can run Python codes in there. All I'm doing is running my simulation on OpenFOAM, extracting data from there, and trying to visualize and analyze that data in Python. So in this workshop, I'm going to follow two examples. First, a simple flow over a square cylinder at Reynolds number of 100. And second, a case of two side-by-side square cylinders with a gap between them. These cases are run on OpenFOAM. They are 2D incompressible laminar and transient simulations run using PimpleFOAM. Uh, I run these cases till they're fully developed and achieved a periodic vortex shading. I chose these two cases specifically because I wanted to show something that I can take under like 100,000 cells, which is, I think, big enough to run on any computer, right? So these are the deliverables that the things that I'll show you in this workshop. Let me quickly just go back to this. If you can still see my screen, I've set up a GitHub repository and I'll just share the location of that repository in the chat box. Do that quickly. Yeah, that's there. So this repository basically contains all the data that's required for this workshop. So if you want to access these files, uh, copy the link that I've sent you and just git clone or download that repository in your local working space and basically just place it somewhere in your working directory that's easy for you to access. In my case, I've just placed those cases uh, at a location, for example, in a place in a folder called workshop. Uh, Now at this point, first let's begin setting up Python. So I've added a requirements text file here in this GitHub repository, which basically includes all the things, like all the Python modules that are necessary to basically recreate these post-processing steps that I'm going to show you. So if you have done Python before, it's simple enough to uh, like load all those modules. If not, like if you don't remember the commands or the functions, I've provided them here. So all you need to do is navigate to, for example, my workspace, and I'll do pip install -r requirements.txt. This file, as I said, contains all the required modules. When you type just enter, and it should go through the installation really fast. In my case, it doesn't need to go through an installation because I've already done that. But in your case, it may take a couple of minutes. So just wait for that to finish. So there are two ways to basically install those dependencies in Python. First, using pip install. Second, using Python pip install. The difference there being that sometimes if you have a lot of different versions of Python, then you can install those requirements in a specific version, whichever one that you would want. So that can be done with additional flags there, but for more general use case, I've just put this command here. Uh, at this point, I'm also assuming that you have a active working OpenFOAM environment in your PC. So in my case, all I need to do is start my OpenFOAM environment using OF 2312. Uh, it like just assuming that you have a working OpenFOAM and Python environment in your PC. So let's go through the deliverables. Uh, if you just check the cases that are available on this GitHub directory, uh, the first case that we are going to use that I'm going to show you is the case of two cylinders at Reynolds number of 75 just 75. We have a post-processing folder with probes and forces. So what I did was I included a couple of probes and I wanted to extract forces on both my cylinders at that point. If you just want to visualize what that two cylinder flow would look like, it would basically look something like this. The animation at bottom right here. So intuitively, I can see that both the cylinders have this amazing vortex shredding behind them, and I don't see any impingement of any of those shredding on each other. So the flow is more or less periodic, steady. Let's go back to the deliverables again. So the the idea behind this workshop and like my workflow is to basically extract the information available in this folder, this post-processing folder, into Python and analyze it. So in lieu of that, we're going to extract and plot the velocity and pressure probes along pressure values along different probes that are given in this file. We're also going to extract and plot force coefficient data given here through force 1 and force 2. Since I will have those two, I will also go on to compute a FFT to get a power spectral density and just check my dominant frequency of the flow using the pressure and force probe data. Further, I will extract and plot data along multiple lines from a simulation. So just to give you a perspective of that, for that part, for that deliverable, I'm going to use the case of a single square cylinder at a Reynolds number of 100. And I'm going to extract information along this center line behind the cylinder and at two lines at 4 and 8D downstream of the cylinder. And I'm going to plot it and just visualize it here. And finally, I'll extract some 2D slice data and visualize it to get a view of the flow field. Uh, After all of that, if we get some time, I can cover some advanced analysis options such as POD, DMD, and animations that I usually write about in my blogs. So uh, if you're following along, I have added a workshop notebook in this repository here that you can download and follow along with me. So let me just open up those cases here, and this is that IPython notebook here. So I'll begin with just loading the necessary modules. First of all, I'll just load the modules that are needed for me: Matplotlib, NumPy, Pandas, and SciPy. OS is a module that I usually load just in case I want to read any files from the system. Uh, Following that, define your paths to where your case is. So if I'm going to use the case of two cylinders at Reynolds number of 75, I'll define the path to that specific case. And I also define a path where I want to save all my files. So in this case, I'll define a folder called figures where I would save all the things that I'll generate here. So I'll begin with my first point. So I want to extract and plot velocity and pressure along different probe points. So for that, I'll use this Python package called FluidFOAM. FluidFOAM project started about in 2020. Before that, I used to use a really coarse version of FluidFOAM, which was called OWL, I think. Uh, which so this package specifically is a package that's designed for OpenFOAM to read different OpenFOAM classes straight from the OpenFOAM into Python. So for that, I'll import my FluidFOAM module, and first there is a command available called FluidFOAM read probes. All you need to do there is define the paths to your probe data, like your post-processing folder path here to your probes. Uh, I want to check my latest time step, so I don't want the startup wake effects. I just want to analyze the data after my fully developed flow. I'll do that here. There are other options available called merge time, which includes both of these folders. For me, the latest time option just includes the folder that's my latest. So using this, I can extract my velocity and pressure probes. So, oh, didn't define the path. Let's go back. Yeah, this works now. So with that, the probe data is extracted. Uh, with this command, we basically give it to three different variables. The first variable defines the location of that probe. The second variable defines the time, and the third variable defines that the velocity, like the values of velocity and pressure at that probe location itself. So you can visualize where those probe locations are. So this locations is basically a huge NumPy array. And with velocity, that probe location is indexed in a way that the first variable is all your velocities. Second variable is the location of your probe. So it's just the index location of your probe. So in this case, number 4 would mean this one. So I'm looking at velocity and pressure at this specific probe location. So when I just execute these two print variables, all I get is first my velocities and then just the shape of my time and the velocity probes. Same thing with pressure. Uh, since pressure is a scalar, my third index will be 0. In case of velocity, my third index can be 0, 1, and 2, since we have velocity in x, y, and z. So with pressure, when I do that, I just get pressure values. And with those things extracted, you can basically go on and plot it using like any simple plotting routines in Matplotlib. So here what I'm doing is I'm plotting the trends of velocity at that specific probe location, and I'm also trying to compute and plot my mean velocity there. It doesn't really mean a lot at this point. Like there is not much significance of that mean velocity at the probe location, but it's just handy that you can do that in Python. You can visualize that in this way. Same thing with pressure. I'll do that and I'll see the trends of pressure, both unsteady and mean flow features. Further, I'll go on to extract the forces. So there is a similar functionality in fluid form called read forces, similar to read probes, which basically indexes these folders, force 1 and force 2, and all it does is indexes this dat file for us. So since I have two different cylinders here, I'll define two force variables, force 1 and force 2, and I'm pointing to two different force folders there. So when I execute those, everything's worked fine, means that it's worked okay. I see that the force is a NumPy array. I'll pass on this force variable to a pandas data frame so that I can basically just structure my data and give each column their specific index variables. Like if you want to know where this comes from, it comes from your this coefficients dot dat file. So if you just open it up quickly, you can see that the first column is time, then drag, then front and rear drag, all those things. So all I do is I write a reduced version of that here and just pass it on to uh, those variables there. Uh, and when I just display that data frame, it would show up like this. So I would have my time, drag, side force, lift, all those things there. Uh, and then you can just simply plot it using common plotting routines. So Here I've passed on a couple of variables like basically plotting my mean force, like mean drag and mean lift uh, for those cylinders. And I get a value of my mean variable there. And I also see the trend of the unsteady drag that's acting, the unsteady drag force that's acting on the cylinders there. So once I have that information, it's really easy to validate it using your whatever way you want to validate it. Here I'm since mimicking the case of March 2017. I've achieved less than 1% difference, so I can call it validated. Same way I can plot the drag for the other cylinder. I can see that the trends are same. The mean drag coefficient is more or less the same. Uh, so in my case, this specific case is refined enough. Uh, Stage 3 is computing FFT. So since I have these drag and velocity signals available to me, I can just pass it on to a simple FFT routine and plot the power spectral density. So when I do it for the velocity, I get this plot with my dominant shedding frequency at 0.15. And I also see a couple of harmonics there. Uh, when I do the same thing for the lift coefficient, I just get one dominant harmonic while my dominant frequency remains more or less the same. And again, I can use that information for validation with that paper that I'm referring to. So here I can again achieve less than 1% deviation. From here on, we are going to use more of OpenFOAM. So the next step is extracting and plotting data along multiple lines from your simulation. So for this, I would go on to my case, which is this one, and I'll just generate a file called multiple lines. This is a function object that's readily available in OpenFOAM. I'll just put information for what lines I want to extract at what different locations. So as I showed before, I'll extract a line along center line and two locations at 4 and 8D away from my prism. And I want to extract velocity, mean pressure, and my Reynolds stresses. So to run this, I'll just go on, open it up in a terminal, and then it's just a case of simply running a post-processing command line function, like function of OpenFOAM. So post-process on multiple lines. When I do that, I let it run and those lines will be extracted here. So if I go back to my case, I check this post-processing folder and I'll see that I have multiple lines folder. And I just want to check my latest time. So I see I have 3 different lines. Uh, these are CSV files which are easy to read in Python. So all I need to do is define my path variables, extract those CSV file locations and their names, extract those lines using pandas, and you can see that I can extract that CSV file here. And then all it remains is to just plot it. And I can see the trend of my mean centerline velocity as well as deficit of velocity, like deficit of time average velocity at different locations downstream. So this is a step of data exploration. So I'm still exploring data from that OpenFOAM simulation using just lines and using quantitative visualizations. The next step is actually doing a bit of qualitative visualization. So I'm going to utilize the surfaces function object. And before that, I'll just run a post-processing utility for vorticity to extract vorticity. In these cases, I've already done that. So I'll extract vorticity for all the available time steps, and then using the surfaces function object, I'll I'll just I'll extract a 2D slice at the center plane at Z0 of my case to just visualize the field, the flow field at that specific location. And then you can simply run post process surfaces. When I do that, it will extract the surface information in a VTP file. And if I go back to my post-processing folder, I'll see the surface information here. And this file basically contains the field data. Let me just check time. I'm at 24 minutes. I'll quickly try to conclude. So to work with a VTK file, I'm going to use PyVista. This is another powerful module in Python that is designed specifically to work with VTK, Visualization Toolkit, uh, where you can read data from a VTK file. So go on and import the PyVista module. I will specify the location, the path to my surfaces folder, and then check my files, that VTP file that's available there, which is this one. And then I can follow the routines available in PyVista to basically just extract data from there. I can see that I have velocity, pressure, and vorticity. I'll just extract vorticity on velocity here, and I'll just plot that using simple matplotlib routine, and I can see the whole flow field here. Uh, this covers the fundamentals of this workflow. Now I'll show you in extension what this workflow can be used for. So if you can extract the field information from one time step, you can actually do that over multiple time step and stack it in this X, which is a snapshot matrix, which is like a long, skinny, thin and skinny, tall matrix. And once you have that matrix, you can perform proper orthogonal decomposition. It's just a matter of using matrix operations like in Python, and you can do the modal decomposition as such. You can also do dynamic mode decomposition using that data, and with enough snapshots, it would give you uh, enough versatility for TOD and DMD both. I've also used this specific workflow to perform bispectral mode decomposition and spectral proper orthogonal decomposition also. So uh, this workflow just works for me. I'm sharing it with everyone through my blogs so that more people can use it. That what motivated this was that I have struggled a lot with Python and OpenFOAM, and this is a way for me to basically help other researchers not struggle too much. With that, I will conclude my training. I think I'm exactly at 27 minutes. I'm a bit over time. Uh, if you have any questions, please feel free to ask me, or I have my information available there. Uh, you can even email me if you have any more questions. Thank you.
So I think we have 2 minutes to take a quick question. Some people have raised your hand, but not now. So I think actually in the chat box, they wanted some of the codes which you have already provided through the GitHub link. So you can get the code, just do the git pull and you will get the whole repository. If any of you have a quick question to ask, please raise your hand. If not, please, as I said, please keep your queries posted in the chat box and the speakers will try to actually. Okay, there is one question. Can we model transient phenomena? How difficult it is? I didn't get the question properly, but Subham, do you want to
So
comment on that?
if I understand, like, so trying to understand. So when you say model a transient phenomenon, uh, as I said before, like I'm doing analysis in OpenFOAM. So all the modeling is happening in OpenFOAM. Python is only used for data extraction and post-processing. But if I can understand that question in another way is I can visualize things, like I can visualize the transient phenomenon using this workflow. So sure, that is possible. So as I showed with POD and DMD data, if you have enough time steps, you can extract that information, and it's only a matter of visualization. Does that answer your question? Sorry, I can't hear you.
Thanks, Subham. So basically, I think if there are any other questions, please keep an eye for some time in the chat box, and I
Sure,
request you to answer them in the chat
sure.
box.
All right. Thanks, everyone.
Right.